Well, good morning. My name is Victor Pozsgay. I'm a postdoc in the geography department, and today I'm very glad to present my research on predicting landslides in permafrost areas thanks to numerical simulations. So funny thing, it turns out I'm actually a theoretical physicist, which means I studied big universe topics like dark energy. But I also come from the French Alps, and I have a deep love for the mountains. And I feel like these different aspects of my personality are really what brought me into northern science and more specifically into permafrost studies. I then came to hear about the growing impact of permafrost thaw in the Canadian North and how landslides in particular are getting increasingly bigger and more frequent. And this convinced me to study them. So this is a picture I took in August close to Dawson City in the Yukon, where you can see a huge slide. Oops, sorry. And here's another angle to give you an idea of its sheer size. And I guess the most frightening aspect is that in the current state of research, can really in the north, it can really happen anywhere as long as you have a slope and at pretty much any time. And realizing this really convinced me that it's an issue that's worth being tackled and that northern communities need all our help now. So permafrost is nothing more than ground that remains frozen for at least 2 years, even in the summers, and it represents about 50% of Canada's landmass, hence the great importance of studying it. So what happens on slopes is that permafrost really acts as a glue that binds rocks together. However, with the effects of climate change and mostly with air warming, permafrost is thawing and hence the rocks lose their cohesion and everything falls down. And since landslides are increasingly affecting Canadian northern communities, then there's a real need to predict where and when they can happen. So just to put my work into context, I'll focus on the example of Dawson City in the Yukon. And what you might not know, and actually many inhabitants there even don't know, is that the city is believed to be under reasonable threat from landslide. This is a picture I took from the top of a hill that's at risk of producing a landslide and damage the northern end of the city. However, on the other side of the Yukon River, there's that other hill that also threatens to slide into the river this time and trigger a tsunami that would submerge the greater part of the city. And when you hear about a tsunami risk in the middle of the Canadian North, it might sound a little like science fiction, but this is the reality of the situation. My project is really part of a wider community effort, so someone locally might observe some unusual sightings on a slope, for instance, and raise their concerns. My project is then to simulate the ground and permafrost and produce landslide predictions that will in turn help the local government evaluate risks and plan ahead. But it's also in touch with reality because I go on the field to help inform model results. So how does it work in practice? The first thing is to get atmospheric data from satellite and weather station, for instance. And then this is really where the magic happens. So I can use my maths and physics background and simulate, and which makes for a very interdisciplinary approach. So this is a screenshot of my screen from last week to give you an overview of what it might look like. It's very colorful. And finally, this helps me make informed predictions for permafrost landslides. So this is an example of what I can produce. So on the x-axis, we have the mean temperature of the ground historically. And on the y-axis, we have the change in temperature in recent years, and there is a very clear negative trend. On the right, we have simulated grounds that started warm, but whose temperatures have barely changed. Whereas when we move to the left, we're now looking at originally cold grounds. But those are experiencing a pretty extreme warming. And hence, the colder the ground is and the faster it warms. And I need to stress that this is actually a new discovery from my simulations, and it also demonstrates the usefulness of simulating in getting meaningful data. And I would like to conclude with another visual that I find pretty striking. Here we're looking at deviation of temperatures and precipitations away from their expected seasonal mean. And really, extreme values of precipitation, air, ground temperatures are known to trigger landslides. And such extremes are here depicted when you're way above the zero line, which is exactly what we see for the water production. And it coincides very, very closely with the timing of a landslide. And I believe it's a takeaway that talks for itself. We can identify landslide triggers and hopefully protect northern communities from imminent risks.